Good afternoon. My name is Mateusz Nytko, and today I will talk about Inter-Iris XI as a platform for scientific computing. Okay. At the first, I want to tell about accelerators. And during the evolution of computer architecture using scientific computing, we can observe two main trends. The first is connected to increasing the number of computing cores and wide register units in CPU. And the second coincides with the use of with the accelerators used to speed up the most demanding problems of code. In the development of the modern computing accelerators, most of the architecture used the NVIDIA architecture. And as you can see in the graph, most of them are NVIDIA. And the first NVIDIA architecture is Xeon 5. Sorry, it's not NVIDIA, it's Intel. And Intel started to want to take part of the market and start to develop his own graphic card architecture. And in 2010, he developed Xeon 5. It's based on knife corner architecture. And this architecture was advertised as an architecture that could combine the power of GPU acceleration with the ease of programming that have this processor Xeon 5. Xeon 5 was a significant part of the most powerful computer system in the world, and in June 2015, the usage of the accelerator reached 44% of all system or acceleration. Even though Intel Xeon 5 architecture was officially discontinued, its evolution led to the Intel XE architecture. Okay. In Intel XE graphic, we have four types of this architecture. It's Intel XI LT is the low power architecture used in a laptop. It's a Intel IP, it's high performance. Intel XE HPG, and Intel HPC is for data center and more scientific usage. Okay. In our developed, we used Inter-Iris XE. Sorry. Okay. Here we have an architecture of Inter-XE LP. As you can see, the architecture divided for 6 blocks. Every block contains execution unit. It's 16 execution unit, and every execution unit have all of them is 96. It's the smallest block in the architecture, and it's interesting because every execution unit is also multi-threaded itself. So we execute 7 threads. And we compare the XELP with NVIDIA GeForce 3060. This architecture was divided for 3 clusters. Each cluster have 96 computing blocks, and looks like this. Okay. For our research, we try to resolve the finite element method. It's one of the most challenging engineering tasks in accelerators. What else? Most research of the use of accelerators computing power data focus on the use of GPU. Okay. Here we have numerical integration to And the finite element method is used to compute an approximate solution of part-differential requests and defined for a given. Usually three-dimensional computer, the computer area is divided into several elements with simple geometry, as you see in the picture. The algorithm consists of several loops, which allows multiple optimization, and the algorithm is embracing part, which allows us to easy prioritization on different types of acceleration. Okay. We solve problems for our research. We used geometrically nonlinear elements, prism, and resolved two problems. First is Poisson equation. The second is convection diffusion reaction problems, and we use standard linear approximation for both. Okay. We also used the modular finite element method framework as a primary tool. This is the method. The main advantage is that it's modulate, so we can change the parameters in every module. We change the parameter for global dependent module and approximation module. Okay. We also use PenCL, relatively standard C language extension. It's for programming of heterogeneous system using GPU, CPU, Colby, DSP, and other processors. It's proposed by Apple and managed by Kronos group. Okay. We also have a automatic parameter tuning. It's a parameter which allows us to control the memory. We have eight options. We can change every this option, and I think it's better if I show you in this graph. This 0 and 1 on bottom of the table is turn off or turn on option in our tuning algorithm. We also have in the bottom right corner QSS, and what is this? It's indicate the order of loops in our algorithm. Q is a Gauss points, S is a shape function. And we turn out that the QSS version of the numerical integration algorithm achieved the best result for both acceleration. Therefore, we have prepared the compression graph. The blue line is it's for Intel XE, and the orange line is for NVIDIA. And as you can see in the graph, the NVIDIA is very regular, where Intel is really chaotic. We have the graph, the lines change, and it depends on memory and access to memory we use. The best results obtained are shown in the graph. We can see that QSS and SQS are the fastest. When we use SSQ, it's take a lot of time. And we can see that Iris LP is around 8 times slower than RTX. Okay. Here we have results for convection diffusion problem. It's most resource-consuming task, and as you can see, it's similar to the previous, but in the same configuration, tuning in similar auto tuning options. We have the very same results. Okay, it's here we can compare the results for QSS option for Intel XELP and NVIDIA. It looks the same. It's similar to the frozen problem. Here we have the timing for well, the results as in frozen problem. The RXE are also slower than NVIDIA. And conclusion, Intel XE seems to have a more chaotic nature of execution. This may be due to its more complex design and different memory organization than classic GPU. But we see that potential in Intel architecture, but we hope we can test in the more in the higher versions of Intel cards in the future. So thank you.
Okay. Do we have questions?
Yes. A short remark. I will begin with that. A short question. So basically, what you are saying from all of it, the message is, if you need a graphics card for finite elements, then go for NVIDIA. Don't buy Intel.
For this moment, yes. Yes, for this moment, yes, but we hope the different Intel card, the highest version of Intel XE card, was better than low power version of this card. But it's for this moment, NVIDIA is, I think it's better.
Yeah. Now to the question.
Okay.
It always surprises me when people want to program finite elements. It has nothing to do with computer graphics, with raster and OpenGL things. What is so exciting about using graphics cards and GPUs in order to accelerate things? Why don't you use more normal processors, which are
because
and easier to program?
Because the graphic cards, it's easy to power the calculations. So we can use more cores, more threads, and computing faster than in traditional processors. Because traditional processors have CPU have 8 cores maybe. Here we have 96 cores or more, and NVIDIA have 3,000, almost 4,000 specific cores for calculation.
I know, yes, but let's say if you repeated these measurements which you showed in the last slides on a normal CPU, I think some of them would repeat. No, the graphs.
Yeah, sorry.
If you used not 2 graphics cards for comparison, but one normal processor like Intel, let's say, I think sometimes many of these graphs were shifted in favor of the normal Intel processors.
It depends. Maybe I will answer because I am a core of this. It depends. We have a lot of studies on different architectures, and we also tested the Intel processors. And when you want to optimize on Intel processors, the finite element method procedures, you have to put almost exactly the same effort as on the graphic cards, but the fastest, the better graphic cards, the highest, of course, the more expensive graphic cards, will compute it faster. Even if you use the most advanced optimization on CPU, in numerical integration, you will compute faster on GPU than CPU. But of course, I understand the problem, because in most of the cases, for example, linear solver or the approximation module, when you are running it and you have the code which is highly optimized for CPU, you can achieve almost the same performance on GPU. But in the embarrassingly parallel algorithm like the numerical integration, you would get at least 10 times faster. And if you have the very complicated task, you are computing a lot of these finite elements, everything goes much more faster on GPUs than CPU.
Sure, but the price you are paying is also...
Yes, of course, but I think it's very interesting because nowadays there are a lot of processors with multi-cores. So we have the EPIC, for example, which has 64 cores. You can use it in multi-processor system, and you have a lot of CPU cores, which can be, in most cases, will be faster than GPU. So GPU is slightly in the back, but there are some tasks where GPU is always faster, and numerical integration is almost all time faster than GPU. That's it.
Okay, thank you very much for
Thank
the
you.
presentation.